So I'm trying to talk louder so you guys can hear because I have to walk around. Okay, so today we're gonna start a new topic called random graphs. So far in the semester, we were studying methods for learning graph representations. So the idea was that, for instance, we had a graph. We wanted to, using some algorithm, we wanted to take this graph and construct a representation of this graph as a real vector, real valued vector. And then this real valued vector was going to be used for downstream tasks, for instance, classification of graphs and regression of graphs. So the other set of things similar to the graphs, we looked at how to generate embeddings for nodes, edges, subgraphs, and so on. So now we're going to look at a different type of task, which is in principle inverse or mirror of the representational learning. So what we're going to look at is graph generation task. So in graph generation task, the idea is that we construct a deep neural network, which as input, it takes some embedding vector corresponding to a graph. And then the idea is that we want to construct a graph with that. So let's say that I have some embedding, I call it Zi, and this is basically a d-dimensional embedding vector. And I pass this to some generative model. And the idea is that given this embedding, I want to construct a graph, G. So this is basically the task that we are gonna look for the next few sessions. Now, there are a few things that I want to discuss before moving on to looking at the deep generative models. And in general, before even talking about any machine learning type of algorithms, we want to look at how the real world graphs look like. So the idea is that you have a graph. It has very simple components. Graphs are constructed from nodes and edges, and that's essentially it, right? When you take some graph and you look at it, like some real world graphs, like for example, internet or web or a social network, it seems that you have randomly selected a pair of nodes in this graph and connected them, right? But just look of it, it looks like these edges have been randomly scattered throughout this graph. Now, the question here is that if the edges are in fact placed randomly throughout this graph, or if there is an order that constructs the basically real world networks or graphs. So here is, for instance, the nd.edu, just a part of nd.edu essentially web. And these nodes here are representing different web pages on nd.edu in 90s right now from the work of Barbara Shan-Albert. And these edges are showing which web page is linking the other web page, right? So when you look at it, you can't really see an order here. There's some order for visualization, but in general, you can't really see an order here just by inspecting by eye, right? There are, as I said, other things like this, like social networks, for example, how in Facebook people are connected to each other, how on LinkedIn or Instagram people are connected, or in real life people are friends with each other. So now, what we want to do is that we want to see if, in fact, these edges, these connections are placed randomly throughout the graph. For that, we need to construct a model and see. So first of all, we need to identify the characteristics of the real world graph. And then we construct a random graph and see if this random graph, it has the same characteristics. If it has the same characteristics, it means that those characteristics are basically we can explain those characteristics through randomness. But if these random graphs don't have the same characteristics, it means that what we observe in real world graphs is not basically a result of randomness, and there is a far more complex algorithm, basically reason behind that characteristic. So to start, we need to look what characteristics can, what properties can characterize the structure of a real world graph. So the items that we're going to look at are first the connectedness of a real world graph, see how connected a real world graph is. And then we're going to look at the average path length in a essentially real world graph in general. What's the idea with that? And then we will look at the degree distribution, which is one of the most fundamental properties of a real world graph. And lastly, we are going to look at clustering coefficient. So these four are basically some of the most fundamental properties that can characterize a given large graph from real world. So starting with connectedness. So when we say real graphs, we are referring to, for example, things like internet, things like a graph of protein-protein interaction, something that in real life exists, and we just construct the graph to show the interactions between these different components of entities in that system. So, and a system that we see in the real life. So we have, in a real world graph, we usually have a giant component which connects most of the nodes in the graph. And then we have a number of smaller components that it basically connects a small number of the nodes in each basically small component are connected to each other. So if I want to show that schematically, this is what we see. So this is basically a large portion of the nodes are connected in this one of the largest component, and then we have a few small components that only contain a basically few nodes each. Now, for instance, let's look at a real life example. A real life example can be actors network. Actors network is a network of different actors and how they essentially collaborated with each other. So in this graph, nodes represent actors, and edges represent if two actors have been in the same movie together. So let's say that Al Pacino and Robert De Niro played in 3 movies together, so they're basically connected through 3 edges to each other, and so on and so forth. So now this graph has about 449,000 nodes in it. And when we look at it, after connecting these together based off of the movies they have played in, we see that 440,000 of these nodes are connected in the largest components. So it means that if Robert De Niro is connected to Al Pacino, and then Al Pacino has played in a movie with Johnny Depp. So if Johnny Depp has not played in a movie with Robert De Niro, they are still connected to each other through a path basically that basically takes you traverse through another actor. So we see that out of these, about 98% of them are connected to each other, and only a small handful of the actors in this network are not connected to the main component. So for instance, probably there is a local theater and there's, 10 actors that play in the local theater that have never played with any other, company, so they're not connected to any other actors in this network. Now, so that's the case with many of our real-world networks. But in some scenarios, the real-world network is just constructed, and I sometimes say network because network is just interchangeably can be used for graphs. And these are essentially called network signs. So I can sometimes interchangeably use network sign graphs. So sometimes the graph itself is only a single component, no matter what. So there is no small components. And this can have two reasons. One can be based off of the nature of the graph and nature of the system itself. The second can be because of the way we measure the system. So let's say, for example, internet. Internet is the set of essentially hardwares that connect different computers through cables, different routers through cables to each other, right? So each router represents a node. These cables that connect different routers are basically representing our edges. Now, the idea with internet is connection. So it means that internet is there to connect different computers. So if a computer is not connected to the system, it's not a part of internet anymore. So it doesn't have a meaning so that you have something that is not connected to other computers. So because of the nature of the internet, nature of the system, this basically internet is just a single component. Everything is in this large component. The other example is web. Now this time, web is the different web pages and the edges in this. So nodes are represented with different web pages, and the edges in this system are links that take you from one web page to the other. Now, there is the possibility that, there are a few web pages that are not connected. Basically, they are not linking anything, and they're just linking each other, right? So there's nothing in principle that prohibits that. But let's say that how you measure the web is important. So the way to construct a graph out of web is using crawlers. So crawlers are basically programs that start from one web page, and then through the links of those web pages, they go to they crawl into different web pages to map internet. So now, if you use a single crawler in order to map the internet, this means that this single crawler should be able to find a link that takes you from one web page to the other. So if you have used only a single crawler to map web, there's no way you can get to a web page that is not connected to the other web pages, because that's the way the crawler essentially traverses different nodes in that graph. So based on this way, the nature of the measurement this time, if we measure it using a single crawler, our web is only going to contain a big giant component. So now in real world graphs, there can be millions of the nodes, but the average basically distance that it takes you from one node to the other node is not that large. So let's see what even distance means. So let's say that Dij represents the shortest path between two nodes. Let's say that we have a node Vi, we have a node Vj, and then the shortest number of the edges that we need to traverse so that we get from one to the other, let's say from Vi to Vj is called the distance between nodes Vi and Vj. Now, if for a given node Vi, if I want to say the average distance from Vi to any other node in that graph, so it means that you start from that node, you compute the distance from that node to any other node in the graph, and then you're going to deal with the total number of nodes, and if you sum all of them and divide that by the total number of essentially nodes in the graph, you're going to end up with the average distance from node Vi to any other node in the graph. So now if I want to find the average distance in the whole graph, I'm going to basically repeat this process for every node vi in the graph. So I say that I do this inside average, basically this averaging, and then I have a sum over all different nodes. So I average also over different nodes vi, right? So it would be 1/, so the mean distance between any two nodes in the graph is shown by 1/v², sum over all nodes vi and all nodes vj, so of vij. So now this assumes that there is a distance between vi and vj, meaning that the graph is connected. We can get from vi to vj. But the problem is that sometimes our graph is not connected. So we won't be able to traverse from vi to vj, so our distance is going to be infinity. And then if we can't use this to get something useful. So we reformulate our formula in order to remedy that. And to basically reformulate, instead of looking at the whole graph, we look at the components, different components. So we repeat this formulation for different components in the graph. So then, when I say that basically when I select vi, vj, I say these two nodes should be a part of the same components. I call that an, and then the nodes of an are represented by vn. So vi and vj both should be in the same component. And then we average over all the components in the graph, right? So we look at each component, we find the mean distance between any two given nodes in that graph, and then we average over whole components in the graph. And that's going to give us a measure indicating the mean distance in that graph. Now, if we have a real world graph, the order, then basically total number of the nodes in this graph can be of the order of millions, but typically the average path is going to be less than 10, right? Meaning that starting from any node, you can get to any other node in 10 handshakes, basically. Now, some people might say that maybe diameter of the graph is a better indicator to characterize the structure of the graph. Now, what is a diameter? Diameter is the longest path that connects any two nodes in the graph. So you look at all the IPJs, the maximum of that is going to give you the diameter of that graph, the longest path, right? So the longest, shortest path, basically. Now let's say that we say that, okay, maybe we can use this diameter as some measure for studying the structure of this graph. But the problem with that is that diameter is just giving you the farthest extreme of the degree distribution, basically the distance distribution, right? So if you have this basically distribution over all the ij's that represents your basically distances throughout the graph, diameter is basically the one in the most extreme one, right? So that might not really give you an indication of the average behavior in the graph. So that might not be the most ideal item to use. The other problem is that this can be affected very much by a slight change in the graph. So for instance, you add a node in the graph and this diameter can significantly change. Or you remove a node and this diameter can significantly change. So this won't be able to give you a indication of the average behavior of the graph because it's really sensitive to modifications in the graph. Now, next is degree distribution we want to look at. Degree distribution is the most fundamental property that characterizes this structure of the graph. So let's say that we have this graph, and I want to indicate the fraction of the nodes with different degrees using pk. So for instance, here I have 10 nodes, and then I want to show the fraction of different degrees in this graph. I have, so for P0, indicating the number of the nodes, the fraction of the nodes that have degree 0, we only have a single node that has degree 0. So our fraction is going to be 1/10. Then you're going to look at P1, which I see that we have 2 nodes here that only have one neighbor, so degree 1. So it's going to be 2/10. For 2, I see 1, 2, 3, and 4. So it's going to be 4/10. I see 1 and 2 nodes that have degree 3. So it's going to be 2/10. And then I see only one node that has degree 4. So 1/10 again. So if I sum all of these together, it should sum to 1. 1, 2, 4, 7, 10, right? So that's right. Okay, so now this another interpretation of this is the distribution of different degree sizes in their graph. And let me add this, that there is no other degree size in this graph. So for P5, P6, and whatever after that is, the basically fraction is going to be 0. Now, this pk represents the degree distribution in our graph. Now, what that means is that this pk represents the probability of a randomly chosen node vi in that graph having a degree k. So if you say that this basically P0 is 1/10, or P2, let's start with this. P2 is equal 4/10. It means that if I randomly choose a node in this graph, there's a 40% chance that its degree is equal to 2. So now real-world graphs show a very specific distribution over their node degrees. What's the thing that characterizes this is a heavy tail in this distribution. So it means that if we have I'm basically showing this probability, we have different degrees in one axis. We have the frequency of these degrees appearing throughout the graph on another axis. You will have a distribution like this, where the tail is non-trivial. So it doesn't go, so in an exponential family type of distribution, you will see that your distribution goes to 0 really fast, really quick. But here it's not like that. You see that there is, for a significant amount of basically for a significant while, you will see that this distribution is non-zero. Now, we call that a heavy tail. So in a graph, that means that you have a few nodes that have degrees that are very high. So very highly connected nodes, but a very few of them. These nodes that are unusually high degree, we call them hubs in the graph, right? So now, while there are a few basically hubs throughout the real graphs, the most case scenario, those have very low degrees, right? So that's essentially what basically how we characterize the distribution of degrees throughout the graph. One example that we can show is the different basically connections, aerial connections for different cities in US. So let's say that this is a map of US, and these blue dots, these nodes, represent airports throughout the country for a number of cities. And then these lines are showing if there is a basically a connection between these two cities. There's a airplane flying from one airport to the other. Now, you can see that for most cities, this essentially the degree of the nodes, meaning that the number of the cities you can travel to is very small. There's two here, two here. But there are a few towns, a few cities like Los Angeles and Chicago that are highly connected, while everyone else has a 1 or 2 or 3 degrees. These have maybe, 15 or 16 different cities connected to them. Through these hubs, you can see one can start from any node and in only a few steps, basically, for example, in 2 steps, you can get to the most cities through these hubs. So we see that this aerial map of basically air travel in the US shows a distribution that has a heavy tail. Now, if we take this distribution and we represent that in a log versus log scale, meaning that log of frequency and log of the degree, we see that it represents a linear, basically a line, a straight line. So if I want to put that mathematically, write that using a formula, I should say that ln of our probability pk is equal to negative alpha some slope of ln of k, k being our degree, plus some constant. So this relation shows our distribution in the log scale. Now I have this. I can take the exponents of both sides, and I can get to an equation that doesn't have ln's anymore. I have pk proportional to k to the minus alpha. Right. So this is the distribution equation for the distribution that dominates the distribution of the diagonal, basically distribution of the degrees throughout the real world graphs. Now we call this distribution a power law distribution. And you can see, for example, in the previous example, the aerial map of US airs, basically air travel shows a power law distribution. Now, we said that power law distribution is characterized by its heavy tail, meaning that the number of nodes that have highly unusually high connections, high degrees, is non-zero, and there's always a few of those. So the networks that follow this power law distribution, we call them scale-free networks. So they have two components. They have a core that connects most of the nodes in the graph, and they're constructed of a number of nodes that are connected to the core, like in a filament, like a hair. So long strings, essentially. So last thing that we want to look at is clustering coefficient. Clustering coefficient, which we looked at in our basically start of this semester, as a measure of understanding how well connected the neighborhood of a node is. So to reiterate that, let's say that we have a node U. This clustering coefficient essentially gives you the number of triangles in the neighborhood of that node U. And the way to do that is by looking at the neighbors of node U and see if nodes V1 and V2, neighbors of U, are connected themselves, are neighbors themselves as well. So if they're neighbors, it means that it is going to construct a triangle here. So the more the triangles around a node U, it means that the neighborhood of that node is more connected, right? So to find that, you're gonna look at nodes V1 and V2 that kind of basically that make an edge, and both of those nodes are neighbors of node U, and we divide that by the total pairs of possible pairs of nodes in the neighborhood of node U, which we can show that by 1/2 times du times du minus 1. So that's another basically interpretation for this clustering coefficient is that what if I select randomly, I select two of the neighbors of a node, what's the chance that those two nodes are connected to each other? All right, so let's have our 5-minute break now, and we start from graph generation.